In the last video we talked about subsets and regions in the plane. Now let's see how we apply those ideas to probability. If we use subsets to define probability, that's called doing discrete probability. And if we use regions in the plane, that's called continuous probability. So recall that probability is a measurement of our certainty about some event E. Probability of E equals 1 means we're certain of E. Probability of E equals 0 means we are certain E does not happen. So we're going to come up with a number between 0 and 1 for our probability of E. So the question is, how do we come up with an exact number? For the probability of E. The answer is, if possible, we inspect the objects related to E or historical data. Then we model our certainty about E by comparing it to one of the following two scenarios. There's going to be more possibilities actually, but we're going to look at two for at least the next couple weeks. So in the first case, the first scenario, this will be the discrete case. We decide that predicting E is like choosing a marble from an urn that is a container. Containing blue marbles. So capital B is the set of blue marbles. And white, I'm going to call this B complement, all the other marbles. And seeing if the chosen marble is blue. Then we say that the probability of E is the number of blue marbles over the total number of marbles, which I don't think I gave a letter to. Let me call it capital S. So set S is all the blue marbles and all the white marbles, all the marbles. Now the continuous case is after examining whatever objects are related to E or whatever historical data we have, we decide that predicting E is like choosing a point at random from a region S in the plane and seeing if it belongs to a subregion, say capital B. Then we say the probability of E is the area of the subregion divided by the area of the entire region. Now, when the number of possible outcomes is infinite, we definitely have to use the region in the plane interpretation. We can't use marbles in an urn because there's only finitely many marbles that we would put in there, and that just wouldn't capture any kind of infinity if there's infinitely many values that we could possibly observe. Now let me set up some notation. Let's define S, we'll call this the sample space, to be all possible outcomes we could observe in the phenomenon that we're predicting. And we don't usually say phenomenon, we usually say experiment. So we're predicting what's going to happen in an experiment. Let's call this phenomenon an experiment. Let's let X stand for the outcome that we're eventually going to observe. And for any set, let's say A of possible outcomes, we call the statement x in A. So we observed one of the things in the set A. An event. And we could also call just A the event. So the probability that x belongs to A is our probability that our outcome belongs to A or, to use shorthand, we could just write probability of A and have it be understood that, of course, what we're looking for is an outcome and wondering whether the outcome is an A, but we could say probability of A. All right, so let's do a discrete example. So let's say our experiment is rolling a die. Let's say we're rolling a fair six-sided die that we have inspected. So we've checked that all the sides look straight, and the only difference between one side of the cube and another side is the label on it. So the sample space is the numbers 1 through 6. And the outcome is just whatever number lands on top when we roll. So we could write the probability that x is 6, the probability that we see a 6, or we could just write probability of 6 for shorthand. So this is 1/6. When we say it's just like, when we say it's 1/6, we're saying it's just like choosing a blue ball from an urn containing 1 blue and 5 white balls, all assumed to be the same weight, same size, indistinguishable when you touch them. And we can write the probability that x is odd or just the probability of 1, 3, 5. For the probability of rolling an odd number. So this is 3/6, which is 1/2. because by the symmetry of the die, which we've inspected, just like choosing a blue ball from an urn that has 3 blue and 3 white balls in it. So in each case, our probability is the number of things in the sample space that are interesting to us divided by the total number of things in the sample space. In the first case, when we did probability of 6, of seeing the number 6 after roll, that was one of the 6 sides divided by 6 total sides. In the second case, when we say probability of x is being odd, there's 3 points in the sample space, 1, 3, and 5, that correspond to that outcome, and then there's 6 total points in the sample space, so 3 over 6 is 1/2. Alright, now let's look at the continuous scenario. Let's say we choose a point at random in the region bounded by y equals sine of x, x between 0 and pi, and y greater than or equal to 0. So basically the first hump of sine. And let's let A be the region. So this whole region is S. Let A be the subregion with x between 0 and pi over 6. So this is pi over 2, pi over 6 is about there. So A is that colored region. Now if we pick a point at random in here, what's the probability that it lands in that region A? Well, it's just the area of A divided by the whole area of the region. I didn't name the point. Let's name the point x naught, y naught. So the probability that x naught, y naught ends up in A, or maybe we could just say probability of A is the area of A over the area of S. So the area of S is the integral from 0 to 1 of sine x dx. The integral of sine is negative cosine plus c. So the area of S is negative cosine of 1 minus negative cosine of 0. And the area of A is the same thing, but we're just integrating from 0 to pi over 6. So negative cosine of pi over 6 minus negative cosine of 0. So the probability of our point landing in A is the area we're interested in, which is, let's see, plus cosine of 0 is 1, minus cosine of pi over 6 is minus square root of 3 over 2, and then the area of S is, let's see, plus cosine of 0, which is 1, minus cosine of 1. Oh, I'm sorry, this should be pi. Minus cosine of pi, cosine goes like this, so negative 1. Minus negative 1 is going to be plus 1. So we have, I'll make the 1 a 2 over 2. 2 minus square root of 3 over 2, all divided by 2. So that is 2 minus square root of 3 over 4. And just to check, square root of 3 is about 1.7. So 2 minus that is about 0.3. 0.3 over 4 is a number between 0 and 1, as it should be, because the ratio of this area here to the whole area should be somewhere between 0 and 1. Now the example I've chosen here is maybe a little bit artificial. I didn't really have any real-world phenomenon in mind that was going to be exactly like choosing points underneath one hump of the sine curve. But the idea is that after some amount of investigation and looking at historical data, we might decide that some real-world phenomenon is just like picking a point under this curve. And the probability of seeing a certain outcome is just like having that point land in a certain subregion of this region. Now how we actually get this curve from historical data is one of the parts of probability that's a little bit less scientific. It's a little bit like an art. And we'll talk about that more later this semester. The end.